so I have to kind of do my best to represent them both quite well. And so my research is kind of takes place in the kind of the union of these two research groups. And so it's the group, or kind of more applied group, quantum field theory and integrable systems, and this more pure group, representation theory. But of course, there's connections between these two fields, and of course, it's part of my talk to make that more precise. And so I will not give you the complete picture, because both integrable systems and representation theory is very wide topics, and there's many colleagues of mine who have their own kind of viewpoints, their own expertise, their own specializations. So I'll give a rough overview and then a slightly more specialized overview, namely for quantum integrable systems and quantum groups. Okay, and so that's an important class of integrable systems. And so maybe before I do that, I mentioned that kind of the union of these two groups, there's some nice activities at BIMSA. So we have twice weekly integral system seminars, so which also often have a high representation theory content. And we have organized conferences regularly. So in summer, as a satellite conference to ICBS, we organized the conference, see if I remember, representation theory, integral systems, and related topics. So next year we'll try to organize it outside your summer holidays, so more of you can visit. Okay. So kind of a general picture is as follows. So integral systems are particular systems in physics, dynamical systems with somehow maximal symmetry. So that could be forced by the geometry or topology of your system. So that means a large number of conserved quantities if you talk about a classical system, or a large number of sensible commuting operators if it's a quantum system. And so it is not part of the definition, but it's a fact that often also these solutions, they have solutions that are expressible in terms of nice functions, which is of course not very well defined, but it's still, there's a connection with special functions. And so representation theory, so the right-hand side of my first slide, is roughly speaking, when you take an abstract algebraic structure, like a group, for instance, is kind of the basic class of examples, and you study it by seeing how it acts on, how it represents itself on, let's say, vector spaces. So the group elements correspond to linear maps, so invertible linear maps on vector spaces. And so you can do this naturally for groups, for Lie algebras, and for associative algebras. And so associative algebras is somehow a more general picture where you can include the other two categories in it. And so there's different flavors of representation theory. So you can have methods influenced by geometry, topology, combinatorics, many operator algebras, many other kind of connections with other parts of mathematics. And so when you're talking about applications, a key question that you want, kind of a key general question that you want to answer is, how do the symmetries of a physical system, which form a group or some algebraic structure, influence the set of solutions? Okay. And the final comment, which I've emphasized, so I'll come back to it, is that you may have different systems, but their symmetries may have the same underlying algebraic structure. So there's some idea that you can use some kind of algebraic object and look at different representations and learn about different models at the same time. So this is good for efficiency. So you might do a computation in this abstract structure and draw conclusions about several models at the same time. Okay, so that's something that's, well, something that will come back. Okay, and so maybe I'll also say here that there's the connection between these two topics is a nice example of what Hossein called physmatics. So there's many cases where some physical questions have kind of reshaped or reintroduced new topics, new objects in representation theory, and driven this development. Okay, so I want to start now with a bit more precise about quantum mechanics. So kind of as a observation that in quantum mechanics, linear structures are kind of essential. They're intrinsic to the setup. So states of a quantum system correspond to elements of a vector space, observables to sensible linear operators. So it has to be self-adjoint operator on a Hilbert space. And then the measurable values of observable are actually eigenvalues of this operator. So that's how you make the kind of connection. And the scalar products that you can calculate between states determine the probability of that measurement occurring. Okay, and so a very important observation here is that if you have a multi-component system, then the space of the big system is a tensor product of the spaces of the subsystems. Okay, so very kind of simply put with an example. Oh, sorry. If you have a vector space for system A, two-dimensional vector space, so this is a basis, let's say, and you have a vector space W of system B, say four-dimensional, then you can combine these systems into a large system, and then you can form these 8 states. And so this forms the basis for the tensor product. And so it's not the Cartesian product, that would be 6-dimensional. We really need the tensor product to describe the possible states of this combined system. So there will be tensor products. Okay, and so the idea behind the standard approach in quantum integrability is that non-interacting system, you could say that the dynamics are reducible to one particle processes. There's no interaction. So each particle is on its own, which is kind of boring, right? But so the next level up, it becomes very interesting already. So we want the dynamics to be reducible to 2 particle processes. So what does that mean? So let's have some kind of slightly toy model. We have n particles moving along one-dimensional space, and they're scattering. So what by scattering, I mean here that the momenta are preserved, but the internal states of the particles may change. So they keep going, and they possibly exchange information by adjusting their internal states. Okay, and so I can take the state space of one particle, let's call it V, finite dimensional complex vector space, and I can think of there being an invertible operator corresponding to the interaction of 2 particles. So this goes from the tensor product, V with itself, to the tensor product. And so what you then expect is that if you have 3 particles coming together, you want to be able to factorize this out into 3 two-particle processes, which can be done in 2 different ways. Okay, and so for instance, on the left-hand side, first the second and the third particle interact, and the first and the third, and the first and the second. Okay, so it's the left-hand side of this equation. And here's the other factorization, right? And it's on the right-hand side. Okay, so this is called the Yang-Baxter equation. This is kind of the key equation in quantum integrability. Okay, there's a slight variation on this, which is quite important enough to mention it here. The R matrices, they might depend on complex numbers, let's say 2 complex numbers, which we associate to these lines. And so they may be a function of the momenta, for instance. So they are preserved. The particle 1 keeps this value Z1 along the line, also after scattering. So there could be complex numbers. And so really what you get here is a family of different solutions of the Yang-Baxter equation, let's say parameterized. And so in order to make it interesting, you must make some requirements on the dependence of this parameter. So let's say they're meromorphically depending on parameter. So there could be points where the R matrix is not defined. And you also want to maybe require that the R matrix is generically invertible. So invertible at most points of this complex, for these 2 complex variables. Okay, and then there's, you want actually to formulate commuting operators. And there's 2 canonical ways to do this. And so the one that's closest to the picture I've just sketched with the scattering is this kind of scattering matrix. So what you do in any case is you put the system on a circle. So you impose periodic boundary conditions. This is the easiest thing you can do. And then you can have the idea that the ith particle of a group of n particles goes for a walk and intersects, scatters with particles, goes around the back of the circle and comes back on the other side there and scatters with some other particles and comes back to its starting place. Okay, and so that's a product of R matrices, the combined linear operator. And this is called Young's scattering matrix. So this was, let's say, investigated deeply by Yang, and these operators for different values of I, they commute. And this is a consequence of the Yang-Baxter equation. It's a nice homework exercise. So there's a different construction, which is actually closely related, but originates more in statistical mechanics. So you have two-dimensional vertex models. So you have basically a square lattice. You split it up into rows, let's say, and you assign to each junction of vertical and horizontal lines a linear operator. Again, with the same idea, it starts with a tensor product and it sends it to a tensor product. And you can then, let's say, compute things like the partition function of this whole lattice via by splitting it up into rows. And then so one such row is called a transfer matrix. And Baxter investigated this deeply in the 70s and later on. And so here you have an extra parameter z, an extra complex number dependence. And so this is an auxiliary, you can think of this as an auxiliary vector space. And you take this product of R matrices, and then you trace out this auxiliary space. You have a tensor product. And so instead of taking the trace all the way down to complex numbers, you can do it in steps. And you just trace out the first, or in this case, the rightmost vector space. And then you can show again that these things commute as a consequence of the Yang-Baxter equation. Okay, so the Yang-Baxter equation is a guarantee for the existence of commuting operators. So here's just to make it kind of a bit more concrete, here's one example. So eta here, so that the Q is misprint, the eta should be any fixed complex number. And what you get here is a particular solution of the Yang-Baxter equation. This can be verified, it's just a computation. And this originated in the 6-vertex model, which is a particular vertex model, a model on the square lattice, which is modeled on how two-dimensional ice would behave. And so you can kind of analyze how the hydrogen and oxygen atoms in a molecule arrange themselves in this square lattice. And then there are 6 configurations which are possible. And these are the 6 corresponding to the 6 entries here, which are non-zero. Okay?
Can I ask a naive question? Why is it assumed here that you always have this non-degenerate picture? Non-degenerate. So for instance, in the previous one, why can I not assume that I can have a particle interaction where the line Z2 passes through the intersection of Z1 and Z3?
Oh, so you can assume this, but you want to impose that all scattering processes are two-body factorizable.
Yeah,
so
why?
That's the definition. To have.
Oh, okay. So it's,
yeah.
Then it's not. That's the question.
Yeah.
It's not. Okay. Then it's not integral. Okay.
That's it. Yes. It's a very special case where this would happen, but they are very interesting. Okay. And so so here's then this formula for this transfer matrix. It gives you after you've traced out this auxiliary space, it gives you a map from n-fold tensor product to itself. So it tells you something about the system of n particles. And because the transfer matrix commutes, you can look at, say, the expansion coefficients with respect to this parameter z, and they are commuting linear maps. And they include, for instance, the Hamiltonian of a particular well-known model for magnetism, quantum mechanical model for magnetism, XZ spin chain. Okay, but it includes not just that operator, but many operators. So you have a family of commuting operators. Okay, so why should we care about these very special models? So you can study interesting physical phenomena, let's say phase transitions, renormalization, things like this, in quantum integral models, and you can then ignore kind of complicated effects arise in more general, more complicated models. So you can study them in isolation. And so one perspective is that you can maybe do perturbation theory that doesn't start from a non-interacting model, but from an integral model, which is closer to reality. These models, some of them at least, can be realized in condensed matter. This can be done now, has been ongoing for about 20 years, I think. So I'm not giving you the reference of the original experiment which did that, but I'll give you a reference to a good survey article from last year if you want to investigate this more. So these are in particular quantum many-body systems known as the one-dimensional Bose gas. And some examples of these Heisenberg spin chains, they can be realized in ultra-cold atom systems. Okay? And so it's very nice that you have this kind of chain of steps between really experiments, theoretical physics, and then pure mathematics. This is all connected to each other. So you have these R matrices. So if you have a solution of the Young-Baxter equation, automatically you have a particular representation of the braid group on the tensor product of vector spaces. And so you can use these R matrices to compute isotopy invariance of knots. So you have the problem that you have two complicated knots and you want to see if they're the same. You try certain things, you apply certain functions. And so R matrices can give you particular powerful functions to test this. So this is this kind of physics perspective that new structures arose in representation theory that were originated in the question about how to find solutions of this Young-Baxter equation. And so this is really quantum groups, the story of quantum groups. So initially, the first example was found in '83 by Kulisch and Reshetigin. And more generally, a whole class was found by Drinfeld and Jimbo. Now we call them Drinfeld-Jimbo quantum groups. And maybe another type of R matrix, whole completely different perspective here, is that you can also approach or study quantum gravity using these kind of structures. Oh, at least in 3 dimensions. Yes. Yeah. I'm not. There might be a different application, but I think this originally was for 3 dimensions. Yeah, so this was shortly after. So these quantum groups have been around for about 40 years. Have been studied for 40 years, and so they're quite well understood. They have their own kind of, let's say, representation theory questions surrounding them, connections to other parts of pure mathematics, such as algebraic geometry, operator algebras, and so they originate in this study in integrability. And so the question is how to find solutions of the Young-Baxter equation effectively. So this is a complicated equation. This is a cubic equation, and it's basically a linear equation for matrices. Even for a 2-dimensional vector space, this is a very difficult thing to solve. And so the question is how do we find solutions? And we can actually be a bit more demanding on this question. So we can actually ask the question: what if I have actually R matrices mapped from act on tensor products of different vector spaces? So you can easily imagine a quantum integral model of non-identical particles. So then the spaces should be different, and you can ask the same question. And so it's a very short step to a slightly more general question. Can we actually solve, find solutions of this, of these Young-Baxter equations for families of models? So you have a family of R matrices, each describing a family of related quantum integral models. Okay, so this is this universality. So is there some kind of algebraic structure which produces a whole family of R matrices? And so you can study several physical models. And so here's kind of a hint at what kind of objects you might want to investigate. Suppose, just to keep it simple, I take the trivial solution. So you can check just the trivial solution satisfies the Young-Baxter equation. That's just 2 non-interacting particles. But suppose I make a deformation. So suppose I have a number eta, and then I have another linear map on this tensor product and higher order terms. Then you can show by looking at the Young-Baxter equation that this new map R, little r, satisfies this relation in the triple tensor product. Okay, and this is a relation in terms of commutators. And so this suggests that Lie algebras may be of interest. Okay, and so quantum groups are associative algebras which produce solutions of this Young-Baxter equation. So they have a non-trivial universal solution, which I call curly R here, that lives in a tensor product of the algebra with itself. And they satisfy the equation in the algebra. And so I now simply apply representation maps, and I will get this equation in any representation of this algebra. So you want an algebra with a rich category of representations, a nice class of representations. And so there's no official definition of the quantum group, but sort of intuitively, there's a lot of family of examples which are referred to by this term. And so they have this property, and they also are closely related to Lie groups and Lie algebras. So they have an important role in physics. And so we kind of deform somehow the representations of Lie groups and Lie algebras. So you cannot do this. So you cannot deform a Lie group and keep a Lie group. You cannot deform a Lie algebra and keep a Lie algebra. You have to replace it by an associative algebra. And to any Lie algebra, you automatically have so-called universal enveloping algebra. And these are infinite dimensional, yes. Even if you start with a finite dimensional Lie algebra. Okay? And so this R matrix then, this universal solution satisfies the condition that at a particular value of a parameter, it should produce this trivial solution. But in general, it should not be trivial, only at that special point, eta. And so if you just look at the action in tensor products, you get solutions of the Yang-Baxter equation. And so I'll just mention here an important family of quantum groups that were discovered in the mid-80s. And so if you take the universal enveloping algebra of a suitable Lie algebra, and a suitable Lie algebra could be, for instance, simply a finite dimensional simple Lie algebra, or you can take what is known as you can tensor this with this commutative ring of Laurent polynomials, you get something called loop algebra. There are certain extensions of this which are also suitable in the sense that I can look at the universal enveloping algebra and deform it. So I can have this R matrix that depends on such a parameter eta that reduces to the identity for a special value. And so, for instance, you can take the simplest example of this affine type, which is basically when you take G equals SL2, you get the so-called quantum affine SL2, and the universal R matrix of that quantum group produces this 6-vertex R matrix on two-dimensional representations. Okay, and so this is kind of slightly kind of overview of systems on a circle, but then you can say, well, this is not quite satisfactory because in real life you would expect systems, if they're one-dimensional, to be on a segment. It's hard to kind of build, let's say, models in real life where it's actually on a circle. It's more realistic to have segments. So you have an interval on which the particles move, and so you have a boundary. And so you can introduce to this calculus of R matrices, this graphical calculus, a new linear map corresponding to interaction with the boundary. Okay, and so here this indicates the boundary, and here's the linear. Here's the particle coming in and going out. And so I assume it's scattering elastically of a boundary. So this counts as a 2-particle process. So now I want 3-particle processes to be factorizable in terms of 2-particle processes, and then you get this picture. Okay, so you have incoming particles, and they can interact with the boundary, and they can scatter back. But in the meantime, they will scatter with each other in different orders like this. Okay, and so this is what's known as the reflection equation. You impose this to have this factorized scattering when the boundary is also involved. Okay, and so here this is written in terms of linear maps. Okay, so this is known as the reflection equation, was introduced by Chirednik in '84. And so you can use this equation to study systems with boundary, at least with one boundary. And the solutions of this equation are called K matrices. And the name K is just simply because this picture looks like a K. This is simply the reason why it's called a K matrix. Okay, and then you can also form these commuting operators on a big tensor product. And so here are the pictures, a scattering matrix and a transfer matrix. And then the question is, how do I create solutions of such equations? Suppose I already know the R matrix. How do I then find this extra ingredient, the K matrix? And so another hint towards to solving this is that boundaries, when you introduce a boundary, you break symmetries. So you have to be kind of careful that you don't remove all the symmetries. So for instance, if you look at this scattering particles picture, if you introduce a boundary, the kinetic energy will still be preserved, but the total momentum will not be preserved. So you lose some symmetries, but hopefully you keep some symmetries. And so you can then think of the quantum group as a symmetry algebra, and you keep some symmetries, so you have a certain sub-algebra of residual symmetries. And this is what we call boundary quantum. Okay, and so this is the last slide. So I outlined some ongoing work, some recent work. So with Andrea Appel, we developed over the last few years the axiomatics of boundary quantum groups. and the reflection equation and its solutions. And so we can answer the question how to find the solutions effectively for large classes of quantum groups and boundary quantum groups, including these affine quantum groups, for instance. Then there's another kind of project with colleagues from Heriot-Watt University. Baxter Q operators, they are kind of fancy transfer matrices. You can recover all the normal transfer matrices from such a Baxter Q operator. And so they are basically transfer matrices where the auxiliary space is infinite dimensional, a certain time. And we can study them for these quantum integrable systems with two boundaries. And so also with Ljarsik, we are looking at the computation of scalar products in these two boundary quantum integrable systems. And then jointly with Reshetygin and Stockman, we also look at quantum KZ equations. So these are difference equations for systems with two boundaries. And you can think of them roughly as an extra deformation of these scattering matrices. And so we investigate these equations as a tool to study the representation theory of the boundary quantum groups. So that's all I had. So thank you very much.
Questions?
So what about the corners? You described some process with boundaries. What about corners?
Oh, so in this picture, let's say here, I basically think of this. I think of this as time going down. So this is a one-dimensional space system. So it's an interval. However, it's a good question anyway. In vertex models, which are two-dimensional statistical models, you could look at models on a square that is without periodic boundary conditions. But then you can basically avoid the corners by just looking at such kind of interactions with the boundary that don't reach the corners. So that's not necessarily an extra problem, let's say, an extra complication. This formalism, not, but yeah.
So you kind of think of this reflection as the operations. How do you write this algebra? So first of all, what is KU of Z1? What is KU of Z1?
Oh, so this is an operator from U to U. So it's a matrix in this case. U is finite dimensional.
Okay. So are you actually thinking I should think of rays before hitting the wall as the input of the system, and then after hitting the wall as the output? Right?
Yes. So you have a particle hitting a wall. And,
okay. But then why do I have 1 over Z2 interacting with Z1?
So
because that's before hitting the wall, they are both just Z1, Z2.
Yes. So here, for instance, so let's look at the left-hand side. So here you have Z1 and Z2. That's this R matrix. Then the second particle hits the wall and reflects. And so at this point, the second one has Z2 inverse.
All right. It's still before hitting the wall.
It's after hitting the wall.
I got it. Yeah.
And then the last one, yeah. So it's just a careful translation of the picture. Yeah.
Questions? So do you use non-commutative geometry to define solutions to Yang-Baxter?
I don't personally, but there are, so usually what you do is you look at the dual version of the quantum group, which is basically functions or deformed functions on a Lie group, let's say. And then you can make a connection with algebraic geometry. This is yeah, non-commutative geometry, if you like.
You can ask any question. Yeah.
Since you mentioned the braid group, so in our community, there's some well-known work of Vershik, Nechayov, and Bibkov on statistical properties of grade groups in locally free approximation used in communication math physics. But they have various open problems, which I wonder if this kind of understanding coming from your
that sounds very
area
interesting. I would appreciate if you send me
I will send you
the paper, or yeah. Thank you.
More questions? So what does it mean, the scalar product? Scalar product,
Yes.
What does it mean?
Oh, well, I mean, it's an inner product on this Hilbert space.
So you just dualize and look at the tensor product. How do you define it?
Oh, sorry, on the tensor
monoidal
product.
category.
Oh, okay, on the tensor product, you just take the product of the yeah.
Bart,
Yes.
so in an architecture case, you know that any solution can be right, some class of solution can be right in terms of cluster variable.
So say this first bit again.
Some class solution of RTT equation can be right in terms of cluster variables.
Yes.
Do you know the same approach for reflection case?
No, I don't think this is investigated. It's this.
And
so about cluster variables. So you mean like cluster algebras?
one of them.
Yeah.
Both case, quantum classical both case.
Yeah. This is So it's This, for our matrices, this connection exists, but for K-matrices, I'm not aware of anything. This is an interesting question.
Okay, if you continue our time question, can we consider kind of on this algebra as also kind of non-commutative geometry structures?
Yeah, I mean, you can do the same thing. You can.
Does people do it? I mean, that is done. I mean, do you know any answer in this direction? Any standard structure?
So you can do the same construction where you dualize algebra.
Not the same, yeah.
Well, it's an analogous construction where you can look at, let's say, it's probably would be algebra of the deformed algebra of functions on a subgroup.
Ah, okay, I understand what you mean.
Maybe a fixed point subgroup.
Maybe for someone who doesn't work with this, when did you quantize the group?
So the name quantum group, so it's a bit of a misnomer, but in some sense it's natural because of this problem that Lie groups do not deform, and so clearly with relevant clearly because Lie groups are so important in physics to describe symmetries, this was wanted in some sense, and so it only was in the 80s that people realized how to actually do this in the right way, and the name quantum group just was natural for them, I think. So, but it's so it's you have to take the Lie algebra, then take the universal analytic algebra, and then in the category of associative algebras, then you can deform it.
Any more questions? Okay, if not, let's thank Bart again.
Thank you.